Alright guys, we are starting video 4 on gases. Hopefully at this point in time we feel fairly comfortable on the idea of what a gas is, why they behave the way they do, what pressure is, what temperature is, how temperature is related to kinetic energy, how kinetic energy and mass relate to the speed of the gas. And hopefully we feel fairly comfortable with using our gas laws, whether it is Boyle's, Charles, Gay-Lussac. Combined are the ideal. Now keep in mind 9 times out of 10 on the AP exam you will be using the ideal gas law, but you can use the other ones as shortcuts depending on the problem. You just have to read and be careful. Starting on a law we have not talked about and you really won't use per se in this format, but just something that we can kind of get an idea of because it will help us in gas stoichiometry. Which again is a very important concept, which we did do last year, but now this law allows us to make some different assumptions. So Avogadro, which we should know that name from Avogadro's number. Avogadro actually came up with his number through the study of gases. But Avogadro's law says that for a gas at constant temperature and pressure, the volume is directly proportional to the number of moles of gas. What does that mean exactly? What that means is when I'm going through and doing stoichiometry, let's say I have 1 liter, there we go, sorry about that. Let's say I have 1 liter of a gas, and let's say I am dealing with the equation hydrogen plus oxygen forming water. And let's just assume all of these are gases. And let's assume I have 1 liter of hydrogen gas. What this allows us to do is recognize that liters for gases can be used interchangeably for moles. So instead of having to convert liters to moles to figure out a conversion from hydrogen to, let's say, oxygen, I can actually use liters in my train tracks. And this is only true for gases, so keep that in mind. So let's say I have 1 liter of hydrogen. Our mole ratio now becomes a liter ratio because of this proportional idea between the number of moles and the number of liters. Okay, and I can say for every 2 liters of hydrogen, I get 1 liter of oxygen, which therefore means if I have 1 liter of hydrogen, I need 0.50 liters of oxygen to be able to react. So really the same idea as using moles, but now we can do it in liters. And again, this is very important for gas stoichiometry, and it does simplify our math to some extent or another depending on the problem we're working on. So let's look at another one. Okay, let's say gas stoichiometry. And of course, we already should be comfortable with stoichiometry. We should be very comfortable with the idea of writing reactions and moving back and forth between reactants and reactants, products and products, reactants, products, products to reactants, etc. Remember, stoichiometry doesn't matter where we start or where we're going. It all works the exact same way. So with gas stoichiometry, we can either be in moles, like what this guy is right here. We could be in liters, and we could also be in grams. It all kind of depends on what we're given and where we're going. Okay, so just kind of some simple examples down here. How many liters of ammonia can be produced when 12 liters of hydrogen reacts with excess nitrogen? Let's actually, sorry, making sure my volume's off because otherwise it makes noise. Just kind of pull these down and work through these. So liters of ammonia can be produced from hydrogen and nitrogen. So we have hydrogen, which of course is a gas, nitrogen, again gas, going to NH3, which is also technically a gas at room temperature. So in terms of balancing, 2 and 3, and remember we're in liters, so we're able to use that idea of moles and liters being proportional to actually be able to do this math. So we just set it up. 12 liters of hydrogen reacts with excess nitrogen, so not a limiting reactant. We want to know ammonia, so for every 3 liters of hydrogen, we have 2 liters of ammonia. So we end up with 12 times 2, 24, divided by 3, we end up with 8 liters of NH3 for this problem. Okay, let's keep looking down at some of the other ones we have here. Okay, how many liters of oxygen can be produced, or how many liters of oxygen at STP can be collected, from the complete decomposition of 50 grams of potassium chlorate? So we write our reaction, potassium chlorate, and this is one of the ones that you would have had to have known the trend for from last year, so you're not going to have a predicting products one like this necessarily, but this is going to form a metal chloride, so potassium chloride, which is a solid because it is an ionic compound, just like potassium chlorate is a solid at room temperature, plus oxygen, which of course is a gas. Now keep in mind, our liters and mole proportionals that we've been dealing up here are only true if we're dealing with a gas or dealing with gases. So this 50 grams down here of a solid, we have to understand that we have to convert that to moles. Also keep in mind, STP tells us something. If you remember last year, we talked about the fact that at STP, oops, sorry, let me rewrite that. At STP, 1 mole of gas is equal to 22.4 liters. So keep in mind, moles and liters are not equal, they're proportional, which is why we can make these assumptions and use them like mole ratios. But in technicalities, the amount of moles and liters are not equal to each other. And this is only true, this statement is only true at STP. So you have to either be told you're at STP, or told that you're at 0 degrees Celsius, or 273 Kelvin, and 1 ATM. So let's work through this. We are going from 50 grams of potassium chlorate, 2 liters of oxygen. There we go. Okay. So first and foremost, we need to do our conversion. We need to do our train tracks. Okay. Which means converting our grams into moles. I get a molar mass for potassium chlorate to be 122.55 grams per 1 mole. From there, we are trying to get into moles of oxygen, and I forgot to balance this, so let's just jump back up here and balance it. I have 3 oxygens and 2 over here, so I know it's going to go into 6, so 2 and 3, and 2 here to get our potassiums balanced. So for every 2 moles of potassium chlorate, we have 3 moles of oxygen. Now, technically, we do have 2 ways we can do this. We can stop and get our moles and plug it into PV equals nRT, where we know pressure is 1 atm because we're at STP, temperature is 273 Kelvin, again at STP. R is a constant. We would have just calculated our moles, and then we would just calculate our volume. R, because we're at STP, we can use this concept up here, which says for every 1 mole of oxygen, again, this is only true when we're dealing with gases, we have 22.4 liters. So when we go through and do this math, we end up with 50.0 divided by 122.55 times 3 divided by 2 times 22.4. 3 proper sig figs because of our 50.0 here. I am getting 13.7 liters of oxygen if I did my math correctly. Okay, let's check out the next one. Okay, how many liters of oxygen gas at 37 degrees Celsius and 0.930 ATMs can be collected from the complete decomposition of potassium chlorate? So notice it's the same reaction as above. Potassium chlorate decomposing into potassium chloride and oxygen. And again, we have our balancing, so 3, 2, and 2. These guys are solids, solids, and gas. Also notice we are not at STP anymore, so this will not work. We're not able to use that 22.4 liters. That is only a true statement at STP. So what do? Well, thankfully, our numbers are going to work out nicely because they're the same ones from above, so 50 grams of potassium chlorate, which we know the molar mass from above is 122.55 KClO3, and that's per 1 mole of KClO3. And now we have 2 moles of KClO3 for every 3 moles of oxygen. Now, we're wanting liters. We're not at STP, so what do? We're going to have to use the ideal gas law in this situation, which means what do I actually want from my train tracks? Do I really want to keep going into grams? No, because grams is not in my equation. I actually want to stop at moles right here. So let's do our math. 50 divided by 122.55 times 3 divided by 2, I get a mole value for oxygen of 0.612 moles of O2. Now, what do we do with that? We plug it into PV equals nRT, where P is 0.930 ATMs, where V is what we're trying to find, N is 0.612 moles, which is what we just calculated, R 0.0821, and remember we do have multiple R constants. I'm using this one because I'm in ATM liters, moles, Kelvin, meaning these are my units I have to be in for this R constant to work. And then, of course, I'm told 37 degrees Celsius, which cannot be in Celsius. I do have to convert it into Kelvin because of my K here. So 37 plus 273, I get 310 Kelvin. So what do? I plug and chug. So 0.612 times 0.0821 times 310 divided by 0.930, which is isolating my V, and I get a volume of, with 3 proper sig figs, 16.7 liters of oxygen. Okay, now from here, we are going to actually look at an AP level problem, but I'm going to stop this video for right now, and we'll come back and look at the next video in just a moment. Thanks, guys.